Hello everyone, welcome back to Abstract Algebra. Today we're going to talk about P groups, but before I start there, let me say why I'm interested in P groups. The goal for the next few lectures is to prove what we call the fundamental theorem of finite abelian groups. And this is one of the big steps in our goal in abstract algebra. We said our goal is to classify all the groups up to isomorphism. And what the fundamental theorem says that if you have any finite abelian group, then G is isomorphic to a direct product of cyclic groups and precisely exactly isomorphic to one like this. So it is a direct product of cyclic groups of prime power order for some P1 through Pn, which are primes, which for the uniqueness of the isomorphism class, I'm writing in increasing order, and the powers to some exponents, such that also for uniqueness, if I have a repetition of primes, the prime may be repeated. If I have a repetition of primes, then the exponents are also to increasing order. And by the way, if G is one of these, is because, well, the size of G is the product of these primes. So this theorem is going to tell me exactly what are all the possibilities for finite abelian groups of a given order by, if I have order n, all the factorizations of n into prime powers, all the possible factorizations are going to give me possibilities for groups. By the way, the theorem also says that each one of these, this is not isomorphic to any other possibility for other prime powers. So before I go into the proof of this, let me give you what is the strategy, and then I'm going to do an example of this theorem. The strategy for the proof is going to be as follows, which is going to explain why I'm interested in P groups in the first place. So suppose, first of all, that G is of order. I'm going to do the unique prime factorization, so with different primes, Q1 to the A1 up to QR to the AR, with these QIs, distinct primes, and each exponent some natural number. Okay, so in this strategy, what I'm going to do is first find out that G is actually isomorphic to the direct product of what we call the Q primary components, or the P primary components. So in this case, there is going to be an internal direct product of subgroups of G that correspond to each of the distinct primes dividing dividing the order of G. So where, again, these ones is the set of all the elements in G such that the size of G is a power of Qi. So every element in this component, every element is going to have order a power of Q1. Every element in here is the elements that have an order as a power of Q2, etc. And it turns out that for an abelian group, G is isomorphic to the direct product of these, where this is what we call the Qi primary component of G. So that is the primary component. We're going to define this and prove that this is actually a subgroup and so on. But that is step one. And step two is going to be to show that actually each one of those primary components satisfy the theorem. So each one of those, if this is a primary component, then this is isomorphic to Z Q to the E1 cross Z modulo Q to the E2 cross Z modulo Q to the ET, say. Then putting these two things together, each one of those is a product of cyclic groups. So the direct product of all those will be a product of cyclic groups, and that proves the theorem for G. So to prove this, what we need to know first is about P primary components, or these primary components of G, and those are groups where every element is of order a power of one given prime. So that is going to be called a P group. So this right here is what we call a P group. And then what I want to show is that the fundamental theorem of finite abelian groups works for P groups. So in this case, the prime P is Qi, so this is technically a Qi group, but we call them P groups anyway. If every order is of every order of an element is a power of a given prime. Okay, so that's why I'm interested in P groups, and that's where we're going to start today. But before I go there, let me give you an example of the fundamental theorem of finite abelian groups. Why is this helpful? So for example, I'm going to classify all groups of order 200 that are abelian. So we're going to use our theorem, and for that I need to know first what is the prime factorization of 200. Well, 200 is 2 times 100, is 2 times 2 times 50, is 2 times 2 times 2 times 25, so times 5 times 5. And each one of the factorizations of this number into different prime powers is going to give me all the possibilities for a finite abelian group. So, so first of all, if G has size 200, then the P primary component, so G is going to be first isomorphic to the 2 primary component times the 5 primary component, with the size of the 2 primary component is going to be the power of 2 that appear, so 2 to the 3, and the size of the 5 primary component is 2 to the 5. Whoop, not 2 to the 5, 5 squared. 5 squared. Okay, so what I need to know is what are the possibilities for the 2 primary components, what are the possibilities for the 5 primary component, and that will give me all the possibilities. So first of all, for G2, for a group of order 2, there are of a group of order 8, there are 3 possibilities of how to factor 2 cubed. There is 2 cubed, or there is 2 times 2 squared, or there is 2 times 2 times 2. You see it's primes, prime powers, so in this case all just like powers of 2 of increasing order. So either I just have 1 prime power to the maximal order possible, or I have 2, and this one has to be at least this one, so it's 2 to the 1 and then 2 to the 2, or 2 to the 1 and 2 to the 1 and then 2 to the 1. Those are all the possibilities. So by the fundamental theorem of finite abelian groups, what we get is that G2 is isomorphic to either Z modulo 2 cubed or Z modulo 2 cross Z modulo 2 squared, or Z modulo 2 cross Z modulo 2 cross Z modulo 2. Second, for the 5 primary component, I have the possibilities of factoring 5 squared is just 5 squared, or 5 times 5. And again, the main theorem tells me now that the 5 primary component will be either Z modulo 5 squared or Z modulo 5 cross Z modulo 5. And finally, I can put these together. Let me do that in the next page. G will be isomorphic to the 2 primary component times the 5 primary component. So the possibilities are I can have Z modulo 2 cubed cross Z modulo 5 squared, or the other possibility for the 5 primary component, which would be Z modulo 5 cross Z modulo 5. Now, another possibility for the two primary component is z modulo 2 cross z modulo 2 squared times z modulo 5 squared z, or z modulo 2 cross z modulo 2 squared cross z modulo 5 cross z modulo 5. And finally, if the two primary component is z modulo, the two primary is z modulo 2 cross z modulo 2 cross z modulo 2, then the 5 primary component can be this one, or the 5 primary component can be this one. So by the theorem, it has to be one of these 6 possibilities. 6 possibilities. Great. By the way, the Chinese remainder theorem tells me that I can actually simplify some of these into other groups. So for example, 2 cubed and 5 squared are relatively prime. So the Chinese remainder theorem tells me that this is actually the one that is just cyclic of order 200. This one, I can simplify that. I can 8 and 5 are relatively prime, so I can put these together using the Chinese remainder theorem, but I can't put this one and this together because that would be this, and these two 5 primary components are non-isomorphic, so I cannot put them together. But I can do 8 times 5, 40, so this can be written also as 40 cross 5, and that is a different group from the, it's not cyclic. So that is a different one. In this one, for example, I could do, there are many ways to do this, but I could do z modulo 2 cross, and then 4 and 25. This is z modulo 2 cross z modulo 100, and so on. So there are other expressions that you can give these, but in this expression is the one way that we can tell them apart, and is the way the theorem is written, so that we can write each one uniquely in that way of prime powers with increasing primes and increasing order of the power of one given prime. Okay, so let's go for P groups. Let's see what they are and prove something about them. Here's the definition. Let P be a prime number. A group G is called a P group if every element of G has order a power of P. So for example, Z modulo P, every element, so 0 has order 1, which is P to the 0, and any other element, which is non-zero modulo P, has order P. So that is, by the way, Z modulo P additively, or for example, Z modulo P squared Z, every element has order 1, P, or P squared. So these are P groups. Okay. What about maybe we can think of D4. D4 has order 8. So by Lagrange's theorem, Lagrange's theorem tells me that any element, the order of any element is the order of the subgroup generated by that element. It has to divide the order of the group, which is 8. So every element is a power of 2. and that tells me that D4 is a 2 group. It's a non-abelian 2 group, but it is a 2 group. Okay, so what I want to prove today is the following. We're going to start by proving the following proposition, which is the following. I want to prove that a finite abelian group is a P group for some prime P, if and only if its order is a power of P. We just saw that Lagrange's theorem says that if the order of the group is a power of P, every element has to have order a power of P. But if every element has order a power of P, why is it that the order is a power of P? What we are going to need is actually the following lemma, which is a precursor to what we will call Cauchy's theorem. This lemma is actually true for abelian and non-abelian groups, but we're going to prove it today for abelian groups. So let G be a finite abelian group of order n, let's say. Then if a prime P divides n, which is the order of the group, then G contains an element of order P. So let's see how we're going to prove this. As I said, this is true in general. Cauchy's theorem, we will prove this later using group actions, says that if G is any finite abelian group, any finite group, not just abelian, and P divides the order of the group, then there is some element of order exactly P. So this will be generalized as Cauchy's theorem, but let's prove it for abelian groups first. Okay, so here is the proof. Let G be a group of order n. Remember, we're trying to prove that if P divides n, then there is some element in G with order exactly P. So we're going to use a strong induction on n, and we can start with the base case of n equals 1, and the case of n equals 1 is trivially true. There is no primes dividing n, so it is true. The condition is true just simply because there is no primes dividing n, so it is satisfied. Now let's assume that the theorem is true up to n minus 1, and the group is of order n, and we want to prove it for n. There are a couple of cases, depending on whether there are trivial or there are subgroups or not that are non-trivial. Remember that we always have E is a subgroup, G is a subgroup, and if there is something in between that is not G and not the identity subgroup, then this is a non-trivial subgroup. So we distinguish two cases. One, if there is no non-trivial subgroups, if G has no non-trivial subgroups, then what happens? Well, let the order is now bigger than 1. So there is some element that is not the identity. Let A be not the identity, an element of G, and consider the subgroup generated by A. It is not the identity subgroup because A is not the identity and this contains A. So it has to be the entire group. Thus, G is cyclic in this case. But we know that a cyclic group of order n is isomorphic to Z modulo nz. If n was not prime, if n is actually a product of two integers, then R Z modulo nz is a non-trivial subgroup of Z modulo nz. And this would be non-trivial if this is a non-trivial factorization of n, and therefore G must be of prime order. If there were no non-trivial subgroups, so n itself is a prime, and since the subgroup generated by A is all of G, that implies that the order of A is P a prime, with P dividing N. Therefore, in this case, every non-identity element has order P, which is the unique prime dividing G, the order of G. So in this case, we win. So what happens if there are non-trivial subgroups? So the second case, now suppose that there is a non-trivial subgroup of G, and therefore, since it is non-trivial, the order is less than G. So now the order of H is between 1 and n, which is actually within the range of our induction hypothesis. So we can use the induction hypothesis. So now there's two cases to consider. If P does divide the order of H, and the size of H is less than n, then this is the lemma, this is the statement of the lemma in the cases we know by the induction hypothesis. Then the induction hypothesis implies that there is an element G in H of order P. And well, this element is also in G, with the order of G is P, and we win. Okay. So what happens now, though, if H is a subgroup, a non-trivial subgroup that is not of order divisible by P? So now the other case is if P is not a divisor of H, but P does divide the order of G, then how do we prove that there is such a thing? Now, since G is abelian, every subgroup is normal. So H is a normal subgroup of G, and we have then Lagrange's theorem. The order of G is the order of H times the order of the quotient group. So because H is normal, G mod H is a group, and P divides the order of G, P does not divide the order of H. That implies that P divides the order of the quotient group. But the order of the quotient group is also in the range of our induction hypothesis, so we can use the induction hypothesis there. So by the induction hypothesis, there is an element which I'm going to call AH in G mod H of order P. Okay, so that means that AH to the P's power is the identity because it has order P. But by the way, this is A to the P times H, the way multiplication works in a quotient group. So what this means, if this coset is the same as this coset, that means that a to the p is in H. And we do know that A is not in H because otherwise AH would actually, oops, I didn't mean to delete H here. We know that A is not in H because AH has order P. If A was in H, then AH would have order 1. So we have those two conditions. And now what I claim is that actually I'm going to be able to construct an element of order P out of this as follows. So now we have found an element A in G such that A is not in H in the non-trivial subgroup of G, but A to the P is in H. Let the size of H be R, and remember that P does not divide R, so P and R are relatively prime. Therefore, by what we call the Bezout identity, there are some other integers, I'm going to call them S and T integers, such that SP plus TR is 1. That a linear combination that gives me 1. And the order of A to the P has to divide the order of the group, right? Because A to the P is in H, so the order of A to the P has to divide the order of the group where it lives, which is H, which is R. So what is that? That tells me that A to the P to the R, which is A to the P to the R, is 1. So that tells me that actually, oops, I should have changed. There's the same exponents here. This is saying that A to the R to the P is 1. And that is exactly what I want. I want an element of order P. This is the identity in G, right? So let me write it instead of 1 as E, and that's E as E in the group G, which is the same as the E in the group H. And I'm looking for an element of order P, so my candidate is precisely A to the R. I'm going to claim that A to the R has order P, and that's the element of order P that I was looking for in G. So here's the proof of the claim. The order of A to the R, because of this equation, is 1 or P, because A to the R to the P is the identity. So the order is 1 or P. So let's show that A to the R is not 1. Suppose, for a contradiction, that A to the R is the identity. Then what can I do? Then A is A to the, I have an expression for 1, for this exponent 1 here. I have this expression, and this is the same then as A's P T R. And using the laws of exponents, this is A as P A T R, and this is A to the P to the S, and A to the R to the T. But A to the R is assumed to be the identity for now, so this is just the identity, so this is A to the P to the S. But A to the P is in H, so A to the P to the S is in H because A to the P is in H by assumption. We had found that A to the P was in H, so this would be in H, but that would tell me then that A is in H, because here is A is equal to this, which is in H. So A is in H, but that is a contradiction because we knew A is not in H. So that is the contradiction I'm looking for, and that tells me that the order of A to the R is P, and therefore there is an element G, which is precisely A to the R a to the r in G of order P. And that's what I wanted. So now by the theorem of induction, thus by strong induction, the statement is true for all n. And that finalizes the proof of the lemma that if P is a prime that divides the order of the group, of a finite abelian group, then there is an element of order P. So now we are ready to prove the proposition that I wanted to prove today, which is the following again. So a finite abelian group is a P group if and only if if its order every if and only if its order is a power of P. So here's the proof. Remember that P group means that every element has an order, a power of P. So let's go first in this direction. So if G itself has order, a power of a prime, then by Lagrange's theorem, if G is in G, we have that the order of G is the order of the subgroup generated by G. That has to divide the order of the group, which is a power of P, and that immediately tells me that the order of G is some power of P, perhaps P to the 0, perhaps just the identity element, which of course is in G, but every element has a power of P as an order, and therefore G is a P group. On the opposite direction, then we have suppose that G is a P group, and we are trying to prove that the order is a power of P. So for a contradiction, suppose that G is N, and there is some Q, not P prime, that divides N. If there is some other prime that divides N, our lemma implies that there is an element in G of order Q, which is not P, and that is a contradiction because G is a P group. So every element has to have a power of P for its order, but this one has order Q, which is a different prime. So the contradiction is with the existence of this Q. So that tells me that the order of G must be a power of P without any other primes in the factorization, and therefore, the order of G is a power of P, which is what I wanted to prove. Great. So what we've proved is that there is two ways of thinking of P groups. One, an abelian group is a P group if its order is a power of P, or it is a P group if every element has order which is a power of one given prime. Great. So now what we're going to do is, in the next video, we're going to discuss P primary components. So given in a group, let's look at all the elements that have order a power of one given prime and prove that that is a subgroup. And then we will prove that every group is direct product of its P primary components to prove the fundamental theorem of finite abelian groups. So that will be next.